Good afternoon, everyone. It's a pleasure to be here. I'm Lunxi, and on behalf of my co-authors, I will present our work titled Attack of the Bubbles, Straggler-Resilient Pipeline Parallelism for Large Model Training. As the training scale grows, distributed training with parallelism strategies becomes essential, including DP, TP, PP, and other specialized parallelisms like CP and EP. In practice, hybrid parallelism is often deployed, combining DP, TP, and PP, and potentially other parallelisms. In hyperscale training, stragglers are components and are still functioning but slow. The first kind is computation stragglers, often caused by GPU thermal throttling or hardware defects. The other kind is communication stragglers. They are slow network links causing extended pairwise transmission delays. Transient communication stragglers are often caused by transient network congestion, while persistent communication stragglers are often caused by hardware defects, network topology, or cross-data center or region links. According to the profiles by Graham, the two kinds of stragglers differ in frequency, duration, and impact on training. Computation stragglers occur in less than 2% jobs, last for 10 minutes on average, and cause less than 12% job completion time slowdown. In contrast, communication stragglers occur in more than 36% jobs, last for hours, and cause up to 90% job completion time slowdown. For computation stragglers, there have been many existing solutions to effectively address this problem. For communication stragglers, although there are also many works for it, all of them do not address the communication stragglers in pipeline parallelism, PP. While TP is less vulnerable to communication stragglers due to its intranode nature, DP and PP are more vulnerable due to their internal links. Although Greyhound mitigate the communication stragglers in DP by migrating slow links from DP groups to PP groups, it doesn't mitigate the impacts left on PP. So, a remaining important issue to be addressed is the slow communication in pipeline parallelisms. By experiment, we find that communication stragglers in pipeline parallelism can cause significant training slowdown. For example, if a minor communication delay increase, for example, 20 milliseconds, can prolong the iteration time significantly by 500 or 1000 milliseconds. And we identify two root causes. First, cascading dependency bubbles, and second, head-of-line blocking in GPU kernel scheduling. First, let's say cascading dependency bubbles. Pipeline parallelism splits the model into contiguous layer groups called stages and splits the input bench into micro benches and pipelines them through the stages. All these pipeline stages communicate via peer-to-peer send and receive transmission operations. The dependencies in pipeline parallelism are not so trivial. Each microbench goes through 3 phases. When activation flow forward, each stage takes input from the last stage and send output to the next stage. And when gradients flow backward, each stage takes input from the next stage and send output to the last stage. So, a single interstage link with high latency will affect both forward and backward operations. For example, here, a 10 millisecond delay between stage 0 and stage 1 will make stage 1 to start F1, 10 milliseconds after stage 0 finish F1, and forces stage 0 to start B1, 10 milliseconds after stage 1 finish B1. Next, let's take a simple 2-stage pipeline example to see how communication stragglers affect the pipeline. First, as we increase the communication delay from 0 to 10 milliseconds, the iteration time first grows slowly. However, once the communication delay exceeds 10 milliseconds, many bubbles occur in the middle of the pipeline, prolonging the iteration time significantly. So, a single communication delay event could snowball into a chain of idle gaps across all downstream stages, and we call these idle gaps cascading bubbles. So what's the condition of cascading bubble occurrence? During analysis, we identify a critical time interval when stage 0 executes these 4 operations. And if stage 1 finishes another forward and backward sequence before this critical interval ends, cascading bubble occur. For example here, the warm-up forward counts of the 2 stages are 3 and 1 respectively. And when the delay is 10 milliseconds, the interval ends early, so the sequence is long enough and there's no cascading bubbles. However, when the delay increases to 20 milliseconds, the interval is expanded and the sequence is not long enough and cascading bubble occur. So, to avoid the cascading bubbles, we need this sequence to be long enough, and we find its length is proportional to the warm-up forward count difference. So our key insight is the difference of warm-up forward counts into adjacent stages, called pipeline slackness. The intuition is the larger the warm-up forward count difference is, the slacker the pipeline dependency is, and the more cascading dependency bubbles can be absorbed. For example here, the stage 0 and stage 1 have 5 and 1 warm-up forwards respectively. So the slackness between the 2 stages equals to 4. Here is another more general 4-stage example. Slackness between the 3 links are 2, 2, and 4 respectively, and they have different resilience to communicate stragglers. Let's take the former example again to see how slackness absorbs the bubbles. First, let's increase the slackness value from 2 to 3, and we can see the knee points of the performance curve move to 20 milliseconds. Then, if we increase the slackness further to 4, the knee point of the curve further move to 30 milliseconds. And next, we finally increase the slackness value from 4 to 5, and we can find the knee point of the curve move to 40 milliseconds. So, as the slackness increases, a larger communication delay can be absorbed between the 2 stages. So we summarize the following theorem of pipeline delay, that the threshold determined by the slackness and the per computation operation time. If the communication delay doesn't exceed this threshold, the iteration time grows slowly. Otherwise, cascading bubble occur and significantly prolongs the iteration time. For example here, the slackness between the 2 stages equals 4, so it can absorb up to 30 milliseconds of delay. With slackness, we design a pipeline adaptation algorithm. When initializing, because we have no prior knowledge of communication stragglers, so we just maximize the slackness uniformly across all links. Then, once detecting a communication straggler exceeding the threshold, we increase the slackness between the affected stages. For example here, when the slackness equals 2, it can absorb up to 10 millisecond delay. So a 20 millisecond delay will cause cascading bubbles. And after we increase the slackness from 2 to 3, the cascading bubbles are eliminated. Besides cascading dependency bubbles, another impact caused by communication stragglers in PP is head-of-line blocking in GPU kernel scheduling. It has 2 root causes. First, communication kernels can get blocked if NICO transmission queue fills up because the data transmission rate cannot match the data generation rate. For example here, the kernel send F2 and send F3 get blocked because the previous communication kernel send F1 has filled up the queue. Second, computation kernels can get blocked if their preceding communication kernels are blocked. For example, here, the kernels F3 and F4 get blocked because their preceding kernel send F2 and send F3 have been blocked. So to achieve blocking-free execution, we propose to decouple communication from computation. Specifically, we dedicate communication to dedicated process using CPU-side RDMA. First, the communication delegates fetch the received data and transfer it from CPU to GPU. And then the training process only focuses on computation. Next, the output data is transferred from GPU back to CPU, and the communication delegates send it out. There are several reasons why we choose CPU-based delegation. First, naive NICO-based delegation using GPU direct RDMA will introduce interference to computation. As shown in the figure at the bottom, the runtime of some computational kernels is significantly prolonged. So CPU-based delegation can fully decouple communication from GPU kernel scheduling to achieve not only blocking-free, but also interference-free execution. And second, CPU-based delegation will offload activations and gradients to host memory. This allows larger slackness in pipeline schedule to absorb larger communication delays. Combining the pipeline adaptation and CPU-based communication delegation, we designed a system named PIPEMORPH. Once the profiler detects communication stragglers, if they occur in DP groups, the orchestrator first migrates the slow links from DP to PP groups. And then the pipeline scheduler adapts the pipeline schedule according to the profiles to mitigate the cascading dependency bubbles. And meanwhile, the execution plane enables CPU-based communication delegation between affected stages to avoid head-of-line blocking. Next, the question is, how effectively does PIPEMORPH address the impacts of communication stragglers in PP? We conducted our evaluation with settings as follows. First, let's see an actual execution example. We injected a 30 millisecond delay into the link between stage 2 and stage 3. As shown in the figure, compared with the baseline zero bubble, the CPU-based communication delegation helps both PIPEMORPH CPU and PIPEMORPH to eliminate the head-of-line blocking stalls. And the pipeline adaptation algorithm further helps PIPEMORPH to mitigate the cascading bubbles. Then we conducted a comprehensive experiment for a single communication straggler scenario. We inject a delay into a single link, and as shown in the figure, PIPEMORPH, represented by the red bar, outperform all baselines across all model sizes, all delay values, and all links, especially when the delay increases to 60 milliseconds. Then, to quantify the overhead of CPU-based communication delegation, we conducted an experiment without any communication stragglers, and we forcibly enabled the CPU-based delegation as a worst-case scenario. The overhead is mainly introduced by data transfer between CPU and GPU and the slower CPU-side RDMA. Fortunately, the overhead is negligible for the two smaller models and moderate for the two larger models. Finally, we evaluate PIPEMORPH in the wild. We trained a 140 billion model with a 1-hour trace with bursty and fluctuating delays in all 7 links. As shown in the figure, PIPEMORPH outperforms the two baseline, 1F, 1B, and zero bubble with 11%, and 36% throughput gains, respectively. And during a severely congested period, the throughput gains further increased to 30% and 47%. It shows the ability of PIPEMORPH to maintain high performance under a realistic scenario. In summary, in this work, we first identified the two main impacts of communication stragglers on training with pipeline parallelism: the cascading dependency bubbles and the head-of-line blocking in GPU kernel scheduling. And then we present a system PIPEMORPH with two key designs to address these two issues: the pipeline adaptation with slackness and CPU-based communication delegation. Finally, we evaluate PIPEMORPH in various scenarios, demonstrating its reliable resilience to communication stragglers in PP. And this is the end of my presentation. Thank you for your attention, and I'm happy to take any question now.